Yeah, to basically the edge of the table. You're good. Yeah. All right, well, we got to connect. Any better? You can hear me? Can you guys talk there? Yeah, keep going.
Okay. On this side? Sure. Okay. You hear me now? Yeah? Better?
Yeah.
Yeah, I guess you gotta go just so that.
You know what? We don't even need this table.
I thought, this one can be closer.
Yeah, I'm just trying to make it lower so it's not like really like in people's way. Okay.
Maybe if you're gonna stand over there, do you want to put a
Well, I think they're gonna try to walk in front of the slide a little bit, right? I don't want to miss them. How's that, Andre?
Yep.
Good?
Andre, hear me? Yes. Okay. Great.
Go ahead
So
and
let us know.
introduce.
Okay, so we get started. Okay. All right, everyone, please return to your seat. We're going to start now for the mechanical engineering, biomedical engineering, Capstone project presentation. All right, good afternoon. Again, my name is Gavin Chu. I'm an instructor for the Capstone project for the mechanical engineering Capstone and the biomedical Capstone for this year.
Dr. Shu. Easier without.
Okay. All right, so I have 4 groups here this afternoon who will present their work for the past year. The first group, they will, there are 14 members: Evan Frela, Brandon Botchway, Joshua Bila, and Kalichi Iwuchukwu. Their project is titled Design and Development of Composite Tape Screen for Deployment Mechanism of Solar Array. I just want to mention that their project is also the entry to NASA Mines competition this year. And they also have been elected as a final, top 7 finalists for this across the U.S. for this year's competition. Next week, they will know what's the final results going to be. So, hopefully, they will have some bigger news to share later next week. Is it virtual? It's a virtual. I think. It's virtual. So with that, I will just hand over to the team to share their project. Just a reminder that I have a QR code I'll pass around. So if everybody can scan it with your phone and fill out the survey, will help us to evaluate their presentation. And also for those joining online, I will send through WebEx so you can have the link to fill out the survey as well. Thank you, and floor is yours.
Thank you, Dr. Shu. Hey everyone, my name is Kalichi Iwuchukwu, and team members are Evan Crowder, Joshua Dillard, and Brandon Butchwood, and we're from the NASA Mines group. And today we're going to be presenting on design and development of composite collapsible tubular mast for deployment mechanism of solar array. So in our presentation today, we're going to be going over our introduction of our project description, the methods we use, results in this discussion, conclusion, future work, acknowledgement, and our references. So the Artemis project name was given because Artemis was the twin sister of Apollo. And Apollo was the name of the project series that led to the original landing of the moon. And NASA seeks to continue this project, the Artemis mission. And NASA will be landing the first human and first personal colony on the moon using innovative technologies to explore more of the lunar surface. Now, currently, the agency is working with several American companies to deliver science and technology to the lunar surface through the commercial Lunar Payload Services (CLPS) initiative. Now, there are existing different solar space-related systems and deployment systems or structures, but these are used in horizontal and micro gravity environment. But for this mission, NASA requires a vertical position and height of this new design that will help prevent loss of power at the lunar poles, where sun does not rise above the horizon. And to meet this mission's energy requirements, solar array must be deployed above the shadowed region of the lunar south pole.
Thank you. What we have here is essentially a project overview of the specifications that NASA was looking for in the NASA Minds competition for this year. So again, they're looking for deployable solar array. So there were a lot of specifications. We were looking at some that we could both easily attempt with the scope of the project, and that influenced what our design objectives were. So you can see they were looking for a deployable area of about 35 square meters, retractable for relocating, single axis sun tracking, number of retraction cycles, adjustable leveling within 10 degrees of vertical, and our optional 10-meter height extension boom, which we were trying to hit. So these are some of the project areas that we thought we could attempt to address some of the specifications that NASA was looking for. So as you can see, we went for novel packaging deployment, optimized use of advanced lightweight materials, lightweight compact components, and a modular and adaptable solar array concept. Next slide. So going into our literature review, we had to kind of get an idea of like what's the state of the art, what's out there in terms of developing a solar or a deployment mechanism and the mast or the support that would go along with it. So initially we were looking at deployable structures. This gave us kind of a state of the art or an overview of what was available in terms of deployable components or structural components. This is everything from inflatable masts, kind of tension-based structures, and as we learned, some storable extendable members, stem types, which come in a variety there, the stem, bi-stem, and bistable reel components. From there, we looked at this paper from the Air Force Research Laboratory, deployable booms. And this gave us an idea of what we can kind of look for in both the orthotropic materials, and that influenced what we were looking for in terms of the layup configuration of a composite, how we could use it to store elastic energy within the mast itself. From there, we looked into design and testing the bistable booms. This was supremely helpful because we were looking for essentially a composite mast that could support a load or a compressive load that would be the weight of the solar array itself. So this paper had a lot of buckling tests and compressive tests of different size composite masts that we could kind of compare and see what would work for our project. Next slide, please. Right. Thank you. So that led us to look at this advanced deployable shell-based composite booms. This is out of Langley from NASA. So this gave us a great idea of what we can use for the cross-sectional area of the mast. This used what they call a mini CTM, collapsible tube mast. And they were using lenticular cross-section, or I believe they call it an omega-shaped cross-section. And what this did was add a fair amount of rigidity so that the mast itself could resist bending under compressive load. From there, we looked at the more analytical or the the calculation side of things. We looked at this experiments and analytical modeling for design of case spring composites. And again, what this did is it gave us an idea of using classical laminate theory to see what kinds of bistability we could find in the tape spring, which is essentially that it has some sort of stored elastic energy in it, but it was able to be coiled or folded for storage. And this gave us an idea of what type of orientation we can use for the carbon fiber or the composite layouts. You can see here the negative theta, 0 degrees, 90 degrees theta, give us what they describe as a bistable composite tooth mass. And from there, we looked at this paper from MIT. This was autonomously deployed tower infrastructure. So they were attempting a very similar project to ours, but much broader in scope. They were looking for kind of a network series of kind of sensor towers that would be deployed on the moon. So similar in the sense they were looking to deploy something, but the compressive load that they were looking at for either a CubeSat mechanism or some sort of sensor or communications device was much lower. But it gave us some great ideas in terms of what we were looking for in the interface between systems and overall kind of what type of control we were looking for the systems. Next slide, please. Okay, great. So after looking at that, we came up with this kind of total initial concept design over here on the right. So you can see here is there's a platform, obviously a battery for storage there. That orange box on top of that would be the deployment mechanism. And then we have a composite mast that rises up and affixes to a solar blanket fixture. So what we were looking at using was what's called the IMBA. This is interface modular blanket assembly. This is what NASA has been installing on the International Space Station. It's essentially a foldable kind of flexible blanket array. So this was the design of the solar array that we were looking for both the mast and the deployment mechanism. So this is a fairly large project, completing this whole thing. So we looked at what we could actually address in terms of the scope of our Capstone project. Advance, please. And so we decided to focus on both the composite mast and the deployment mechanism kind of twinned together there, and then also the servo control, which would link into the accelerometer sensors and the gyroscopic sensors for a self-leveling feature. So our design objectives were a mast structure capable of rigidity, but also capable of being coiled or folded, self-deployment of the mast, again, via that strained energy that would be stored in the composite. The objective height extension at 1/10 scale, so they were looking for 10 meters. We were trying to hit at least a meter high in terms of our mast. The development and deployment of the mechanism to house a coil mast. So some sort of spooled mechanism that would help it keep it in storage, but allow it to deploy as well. And then for the servo motors, we're looking obviously to calibrate the sensors to determine the vertical position of the mast and the sensor control of the legs, so that when that vertical position fell out of alignment within 10 degrees or so, the legs would automatically adjust the leveling of the platform, leveling out the total mast. Next slide, please. So this is just kind of a design flow chart that we're looking at, because there's a lot of different types of CTMs or composite masts out there. As this helped us decide on what type of design we were ultimately looking for. I spoke a little bit before. We were looking at something that needed a large cross-sectional area, lenticular cross-section, so it could resist bending and have a little more rigidity for the load that we were going to put on it. So you can see here, we decided on a carbon fiber prepeg just because this was a little easier than what's called a wet layup in terms of carbon fiber. This has the matrix or the resin or epoxy already baked into the fiber, so we didn't have to worry about getting kind of an equal spreading of the matrix of the resin, because that plays a part in how the elastic energy is stored too. So we thought something that was already pre-manufactured and had a consistent level of resin was the way to go. From there, we decided on a unidirectional weave. Again, this was looking to store some of that elastic energy in the mast itself. The unidirectional, of course, tension in the fiber is only along the weaves. So by using a unidirectional weave, it only has tension within the composite in one direction. We were looking at what type of layup we could have, an asymmetric layup. I think we went a little bit above 45 degrees due to some limitations in the material we were able to procure. We were aiming for what's called a bistable state spring. So again, this would be capable of being stored in a coiled or folded position around a spool, but then still maintain its elastic energy that could have some sort of self-deployment. It could help itself kind of exit the deployment mechanism that we developed for it. then of course testing the properties after redensation. So in order to do this, we had to verify kind of the design that we were looking at in terms of composite design. So for this, we looked at a lot classical laminate theory. And this was taking some of the material properties of the composite itself, which is longitudinal and transverse modulus, Poisson's ratio, shear modulus, and you could try and anticipate what would be the deployment force of this coiled composite casing. So we could predict strains, displacements, and curvatures in the laminate, and then from that, based on the material properties and the kind of fly setup that we used, we could have some rough idea of what we were looking at in terms of deployment force. Next slide, please. So this was kind of what we were looking at. We were looking at, again, a unidirectional carbon fiber, and the fiber sort of stretches along the weave. So if it's unidirectional, it's only one direction. But by laying it up in multiple layers of plies, we could kind of influence how much energy was stored in the composite structure. So a lot of the literature that we looked at recommended this kind of 45, 0, 90 degree, negative 45, with the 45 angles adding some of that elastic energy, and the 0 and 90 adding a kind of perpendicular rigidity to the carbon fiber mass itself. Due to the limitations of the material we were able to procure, essentially the bolt width of the carbon fiber itself, what we wound up going with was actually a 77 degree, 0, 90, and a negative 77. So we were kind of, go back a little bit. So we were looking at what would be the kind of the extreme threshold of what would be considered a biskating state frame. Once we would go above about 60 degrees, it would start to lose kind of elastic energy as it was coiled or stored. But again, given the material consideration or material limitations, we went for that 77-degree angle, which would still have a pretty significant deployment force. Brandon's going to tell you a little bit about the fabrication process.
Okay, so our steps in the fabrication methodology in our assembly plan were as such. We had to assemble a cure oven, working on mold fabrications. We worked on the inertial orientation system. Then we did our carbon fiber prepreg layup. Then we did our 3D printed components. Then we did our final assembly. So this is us assembling our cure oven to the right. So it was made using insulation foam, photopack insulation foam, insulation duct tape. We had thermocouples for digital reading, and for our heating system, we actually used an air fryer, which gave us the proper temperature and controls that we needed for the curing process. And so for our mold fabrication, as you can see, we have to the top right, you have a negative mold. To top left, you have a positive mold. So the negative mold was placed under the bottom of basically the support structure for our lenticular cross section. Then the positive was layered with the unidirectional carbon fiber, which gives you the shape that you need in terms of the collapsible tube mass. So we used rigid 10K engineering resin. And the reason why we use that is because of the deflection temperature, which is 160 degrees Celsius, which meant that we could put it in our cure oven and vacuum seal it so that the collapsible tube mass could keep its shape cured properly. So we had 6 interlocking parts. As you can see, there is a male and female part to every piece. And so we were able to connect all 6 pieces, cure them, and cure them. So interesting fact about our mold preparation. So initially we wanted to do our largest print with a different radius, but due to time constraints and constraints of our printer, we decided to keep the lenticular radius at ½ inch, and that way we did not have to do, say, extra prints. It saved us a lot of time because each print took about 3.5 days, and that's just 2 negative and 2 positive molds. So for, I explained the process prior to, but once you print SLA. In order for it to retain its strength, you have to take it from the printer. You have to put it in isopropyl alcohol. And you actually have to take off these support structures here at the bottom. And then you have to put them in a UV chair oven. So based off of a previous design Hyundai Rios made prior to, we actually made a UV chair box of the remainder of our insulation foam, lined up with UV lights, and we actually had a rotational disc inside that operated off UV light. So that's how we cured molds. And then also, once you take them out, you have to wet sand them and prepare them with wax and PVA before you put on the unidirectional carbon fiber. And that's just so the positive mold does not stick in the collapsible tube. And so this is just the curing process. So as you can see, top left, it's actually one of the prototypes. You put it in a vacuum sealing bag. In addition, our cure oven on the right, the proper parts that you need for vacuum sealing, we had to create a hole in our oven so that while the part is curing, it can also be vacuum sealed. So once again, retain the shape. At the bottom is our first prototype, to the tube mask, although that one was not very collapsible because we used 8 layers instead of the requirement. Yeah, so once again, the entire process for each sort of about an hour and a half start to actually 2.5 hours from start to finish, because you have to ramp up, ramp down, and you need to wait for the carbon fiber to get to room temperature before you take out the center mold. And then last but not least, this is the component printing that we also did with an SLA printing. What's most important about this is that via Creo, we were able to reduce the weight of our top caps seen here by 30% by introducing a lattice structure. So the parts were still retaining the strength that we needed, but we were able to get the weight down 30%, which was really good for.
Thank you, Ryan. So your UDC Masterminds Wax On Wane Off team was responsible for 2 novel design and implementation processes this semester. One of them is the design and implementation of a collapsible composite carbon fiber extendable and deployable tube, which Brandon and Evan just discussed. And the second is the design and implementation of a self-leveling Arduino-based control platform to house the system. We call the second one our inertial orientation unit. So they're peaks of eternal light, which are theoretical, well, they're hypothetical surfaces on a body where there is constant sunlight. Does anyone want to guess how many there are on the moon? Says 0, Justin? Good guess. So in 2009, we sent a lunar reconnaissance orbiter to the surface of the moon to find out how many there are so we could categorize them. And we realized that there's none. But the good news is there are peaks of near eternal light, and that's where Artemis X will live for its entire surface. So near the craters on the moon, there are areas where the light is near eternal. Specifically, the Shackleton crater is of most importance to us. For our design requirements and specifications, NASA Minds calls for adjustable leveling within 10 degrees of vertical. That way, when our system is on the surface of the moon, we'll always be able to get a level surface no matter where the platform is deployed. So our design challenge is to keep Artemis upright at all times. There's 2 great things that get accomplished by that. One, there's only acceleration in the Z going straight down through the platform. There's no X or Y acceleration, so system components can have a longer life. And secondly, we have a higher solar efficiency because we're directly facing the sun, and we get the highest amount of solar capture. Our engineering prototype design was the first part of our inertial orientation unit. primary objective here is to have a platform that is directly orthogonal with the moon's gravity vector. So the way we accomplish that is by having 4 hard points on the underbelly of the surface that have servo motors attached and that provide elevation using the rotation of the servo motors as legs. We have an engineering drawing that we designed, as well as figuring out what our footprint was going to be, our height when we were in a laid configuration, as well as our height when we were in a standing configuration. For our control system design, we have a process control map here. This process control map, so any acceleration outside the 1.6 meters per second squared, that is the moon's gravity, is interpreted as a leveling error, which will put the system into one of these 8 different correction loops. So the code works this way. We'll start with the 1 here. The first operation is to grab the acceleration in the x and y. As we kind of been talking, the x and y acceleration should always be 0. We have our z from the gravity, but if we have any acceleration in x or y, that means we're tilted. So we get our x and y acceleration using this normalized acceleration function, store them as integer variables in value x and value y, and then map those using a map, which is, you can see here in the top acceleration box. We'll map from values that range from -9 to 9 to values that range from 0 to 180. So we'll get about a factor of a 9 increase in sensitivity. Second part of our code is to name and attach our servo motors. So the way we do that is by declaring each one to a digital pin, and then defining each one to a digital pin, and then declaring each one a pulse width modulation of a value where the system is completely flat. Once we have those two, the most novel thing about our surface leveling platform is probably the third step in our process code, which is 8 different correction loops that are available. So there's a while loop that constantly monitors the acceleration. Anytime the acceleration is interpreted as non-zero, the while loop jumps to a digital control of the servo motors, which is using digital to control a pulse width modulation. So it's like a digital to analog controller. Each tilt condition is numbered here. So there's 4 side tilt conditions and there's 4 corner tilt conditions. The side conditions are a little bit more complicated because they are corrected using all 4 servo motors operating simultaneously. Both ones on that side have to go up and the ones on the other side have to go down. The corner tilt conditions are a little bit less complicated because you only have to manipulate 2 servos in order to get those in the right process. Last thing I'll say about this is that our group at designing this method of surface leveling is the first iteration that we were able to find of this surface leveling. Like a lot of places you can find ways to get surface leveling happening, but this is one way that is completely novel, just in general. After our design, which is what we just did, we went to the integration of our hardware integration. So now we're switching from design to testing. We had to do test for our power requirements, as well as testing to make sure that, soldering components as well in between. But now that we are in our control system testing, there was 2 things in particular that we needed to test for. The accelerometer prints out value vector variables, which have to be converted into values that we can use for a servo motor. So that communication was something we tested, as well as establishing the communication and determining which communication will result in servo motor motion that is desirable. Once we were done with that testing, we finally decided to do our prototype for our base platform. Here, the testing is a little bit more straightforward and mechanical. We wanted to test our torque capacity. So we have a 25 kilogram torque output, which is way more than enough. That test went pretty smoothly. And then we wanted to also try and develop a relationship between our rotational output and our translational motion output as well. So we used a arctangent function to determine what rotational angles gave us what elevation and linear translation. And we also developed a Scott yoke mechanism for the legs for a future iteration if we need more height than the extra 2 inches you get from the servo motor arm. And lastly, we just wanted to show our process control map. We like to think of it as a smart system because anything that has to make a decision, like if you have a box and the box opens or closes based on whether there's something in front of it or not, now it's a smart box. So you can kind of think of our system as a smart leveling system because it does make a decision somewhere here in the loop where we've highlighted in orange. Other than that, we have a digital process control using the I2C communication protocol to communicate with 2 different devices at the same time.
So this is just a little bit of discussion of the results. We did some tensile and compression testing on the carbon fiber mask that we created. You can see here we just have some standardization in the terms of the specimens that we're using for testing. The multi-directional layups that we used were 90-0-90 and 90-45-0. Actually, those are recommended for tensile testing. In order to reflect the actual carbon fiber that we used in our test, we did a 90-0, which is a more rigid configuration, and a 77-77. So just running it through and finding our stress strain curve here, we found a kind of discrepancy in the Young's modulus. I imagine this is mostly due to the imperfect nature in which these kind of specimens were made by us. Interestingly enough, they don't sell carbon fiber dog bones. But we found this discrepancy in the Young's modulus, but that'll result in some future work. Next slide, please. What was really most interesting to us was the results of the compression testing. So we wound up making this kind of mini collapsible tube mask here, this kind of stubby little guy, in order to test it. And so we put it under load, and what we found is that buckling occurred at the midpoint, but buckling was totally elastic. There was no permanent deformation to the tube mass after putting it on compressor stress. And we were looking for something, hoping around, I think, 133 newtons or something like that. And what we had found with this kind of mini CTM is that we actually had a peak load of 1,500 newtons, which is way higher than what we were looking for. Now, obviously, there would be some discrepancy between our full-scale prototype of a meter, let alone the mission mass that would be at 10 meters. But it was very promising in terms of what the carbon fiber, what kind of load it was actually able to take. And so we ran this compressor test a number of times. Buckling always occurred at the midpoint, never at the root or the top. Again, just a standard length. And what we were looking at was the peak load. You can see by the third test, the CTM was starting to get a little worse for wear, probably some cracking along the seams where it's joined, or some maybe some stress fractures resulting from the compressor test. But again, we were pretty happy with what we were looking at in terms of scaling this to the actual 10 meters within the range of what we were hoping for in terms of the compression load that the tape is able to stand. Next slide, please. I'm going to let you know about some of the conclusions.
Yeah, so basically, in conclusion, we developed and fabricated a collapsible tube mass with self-leveling capability. We hit many of the milestones for the competition and with NASA, but with the limitations in our unidirectional carbon fiber and the amount that we had left once we got to our final design, it limited us in certain other aspects that we could accomplish. One of the main points is that with our carbon fiber collapsible tube mass, we had just a lot of stored elastic energy, which resulted in the failure of a spool of our deployment mechanism. We'll discuss that in future works, how we can fix that. So there are other improvements and redesigns to focus on, and have another refocus on in our design. But the most promising part about our entire project was how we used 3D printing to solve a lot of our problems in terms of fabrication, especially for the molds. We had several different ideas in terms of using clay, initially in silicone, but the quickest and best results came from temperature rising. So these are just some of the things that we plan to focus on in future work. So of course, further tensile testing with the proper layups, using ASTM standard guidelines to properly get our results. national process loading and buckling test. Once again, all things that we did, but we'd like to continue them. Calculation of the natural coiling radius, Lamb theory, so that we can actually get a carbon fiber collapsible tube mass that is self-deployable. Then, of course, we want to replace the deployment system, make our schools bigger, kind of just adjust it to collapsible tube mass. And then we want to redesign and fabricate the other ways to better facilitate the carbon fiber. And that was actually the part that you saw that was latticed. And on the redesign, on the deployment mechanism, there should have been a brace that keeps our carbon fiber collapsible tube mass vertical during deployment and retraction, which is very important for solar sail that we can use. So, of course, we would like to thank NASA for all their support and their funding for our project and having us be in the NASA competition. We want to thank everyone from UEC, including group members that were very patient with us as we use the SLA printer for the spring break. So we want to thank Dr. Shu, we want to thank Dr. Pierre, we want to thank Ania Rios, Mr. Pablo Guerrero, of course, he's here, Kevin, very helpful and instrumental, and us getting our parts on time is very important scheduling. So yeah, thank you, and that's our presentation.
Questions or feedback from the audience?
Good job, guys.
Yes, Dr. Tiagi.
Just speak loudly, please. Yeah.
Yeah. So, how much power is the whole system is supposed to produce?
So I think at 35 square meters for the mission prototype, they were looking for 10 kilowatts of power, which just based on the kind of the state of the art of the modular blanket array that they were trying to use, that they've been using on the space station. I think they're employing it sometimes. It's more than capable of producing that type of product.
So, along with solar cell, so there are various types of solar cells.
Mm-hmm.
I don't know, so when you get was there something like which you estimated like it is like 20% efficient solar cell, 50%, 60%?
Oh, for the actual IMBA itself? No, so we were looking to get a lot of the specifications. We were looking at some of the patents that they have for the system. They were keeping both the density of the modular blanket and its total efficiency somewhat secret. We couldn't find it in some of the patent stuff just because I guess NASA's using it now. So what we did is we looked at some commercially available flexible blanket arrays and what type of kind of efficiency we could get from those in terms of the area they want, square meters that they were looking for the deployment. We found, I don't know them off the top of my head, unfortunately, but it was sufficient for the area.
So NASA has access to a lot of high-end solar cell which common people do not use.
Exactly, yeah.
And so that was the purpose of our design, right? So no matter whether you got your solar cell commercially or through NASA, with square meters and how already deployed, you'll get
A very nice concept. Good work.
Thank you, Dr. Gray.
There are many aspects of the design. I think you guys focused on the deployment mechanism.
Yes, exactly.
There are cost of solar cell energy storage actually, for the solar power you collected.
Yeah. There's some dust. So they were looking for lunar dust mitigation, some azimuth control for sun tracking and stuff like that. But a lot of that was outside kind of the scope of the design.
And just a side note, I know we talked about the fabrication of our mast quite a bit, but our focus is really on the deployment mechanism, right? But you can't deploy and retract if you mast. So that ended up taking quite a bit of our time, but it was well worth it. New skills. Take them into our careers.
Yeah, I just want to mention that for this team, they actually have 1 month less than other teams to finish because the deadline for the NASA Minds competition is in March instead of April. So I remember they were working hard during the spring break in the machine shop, in the lab, just trying to fabricate. They have to build the whole cure oven in order to cure the resin, the carbon fiber they built. A lot of work they have put into their project. Right.
Thank you.
Azam has a question.
Yeah. So I'm not familiar with the whole system. So based on the solar system I saw outside our home, there's a angle, right? And one side can be used for the production of energy, right? When you are having this deployable, is it 360 degree or
So, yeah,
is that the mechanism that you are addressing this?
Yeah, we didn't fabricate a rotational mechanism, but initially that was part of our design considerations for the entire concept, was that there would be a rotational control so that the system could pivot depending on hitting the strongest degree of sunlight.
Sure.
Yeah.
Okay. Good job.
Maybe I just ask one quick question. So can each one of you share one thing you learned? Most important thing you learned about this experience?
Yeah. Okay. I mean, we definitely learned a lot about SLA resin printing, but I think probably the stuff that I was not really familiar with at all was the classical laminate theory and just kind of the idea of storing kind of this elastic energy within the composite material. It's like when you think of carbon fiber, you think of kind of these rigid parts. I didn't realize there was such a wide variety of carbon fiber out there available, and that each kind of variety had its own purposes and uses and how that could be used to kind of store energy within the material itself.
I'd say first thing is when working with NASA, you know that they had rules and regulations. We had to do a systems engineering paper, which is a little bit different than the technical paper, and it basically gives you from start to finish how to successfully complete a project. So that project management aspect of a systems engineering paper, I knew nothing about. And so having to delve into that, learned a lot. And also knowing that systems engineering is a field. So as you get into your career, eventually, if systems engineering is something you want to do, once you get the experience, you can go into that, which is exactly what the paper was like. And then, I guess from a fabrication standpoint, we were novices in the type of carbon fiber. So just understanding the differences, types of carbon fiber, how to fabricate them, especially removing the molds, which I think destroyed a couple in the process. It's definitely something that
Probably that if you're going to use an electromechanical system and it's going to move too much. So test it early and just be ready for troubleshooting.
I would say one of the things I learned is during my 8 year at the university, I don't think we've had the opportunity to machine shop as much. So using the machine shop during our fabrication, probably learn a lot from guys in Pablo.
Okay.
So that was pretty good. And it's the overall concept of the project. I don't know. My eyes.
Good. Right. All right. Let's give them a round of applause. So we're a little behind schedule. We started late because previous groups. So we are moving on to the second group. Yeah, the presenter from the second group, you can come over.
Yeah. Oh, the
Okay, so, all right, so the second group we have today, team members, Maria, Kimani, and Ku. Their project is to design and development of a passive thermal management system for electromechanical actuators used in electric aircraft. Also want to mention that they have also worked very hard, spent the entire break in the lab working on building the prototype. I don't know whether you brought some here today, but it should be in the lab, so anybody who are interested, want to take a look, feel free to stop by the Capstone lab and take a look. Okay, so I will.
Dr. Shu, before they start, can you mention also the evaluation?
Yes, so I did monitor the evaluation. So for audience here in this room, please, we have a QR code printed on a piece of paper. If for the people who have it, please pass it around. You can use your phone. Just scan that code. It will take you to the survey link. Please fill out for the group. And also those online are already sent out through the chat box. Or you can log into the WebEx and click the link in the chat box. Also will take you to the survey. Please fill out. It's very important for the AVAT assessment. Okay? All right. Nice.
So good afternoon, everyone. We will be presenting today on the thermal management system of an electromechanical actuator in aircraft. Presenters today will be myself, Kimani Brown, and Doniana Andre Melania, and Uku Bacha. So just to give a brief outline of what we're discussing today, we'll talk about give a brief introduction of what the project is about, giving a description. Then we'll move on to the literature review, where we'll showcase the ideology behind where we got the ideas and how to develop our project, and discuss previous work that has been carried out, the methods and computational approach that we use to solve the problem that we're facing, the results that we gathered, and what we understand or discussed from the results, and finally go into the conclusion. Next, we'll talk about the future works and acknowledgements, and then
So first, I'm going to start off the introduction and project description.
All right, so presently the aviation industry is working towards hybridizing and eventually fully electrifying aircraft. And there's a lot of benefits to doing this, such as elimination of direct carbon emissions. You're also looking at about 90% reduction in fuel costs, and you're also looking at reduction in noise pollution when operating the aircraft. With this motivation in mind as well, they are also seeking to replace the hydraulic actuators within a aircraft with electromechanical actuators, or EMAs. Before I'm going to go into that, I will just like to mention that the purpose of actuators within an aircraft is to essentially move the flight control surfaces, which you can see, there's an example of one here. It's the slide right here. They essentially provide the actuation force required to move the flight control surface in order to help with the trajectory and lift control of the aircraft. There are also some other benefits to using an EMA rather than using a hydraulic system, some of which include the fact that it is more compact and lighter weight compared to hydraulic systems. You're not looking at any heavy hydraulic lines being implemented here. You're also looking at a lower maintenance cost. It is also very energy efficient, since it only requires power on demand, and it's also a lot more cost effective compared to implementing a hydraulic system within an aircraft.
So just to touch a bit more and give a better understanding of why an EMA is better than a hydraulic system. Key things that we chose to highlight here are, so key things that we choose to highlight here is the fluid costs, the total cost of operation, the pump cost, and the overall footprint that the system takes up. So as you can see, the fluid cost of a hydraulic system starts off in the range between $31 $75 per gallon to $188.44 per gallon, which is the scheduled hydrate fluid, which is most common in most commercial airline crafts right now, which is the fluid that's used most commonly. And to fill the reservoir required for the operation of these systems requires 15 gallons, which amounts to a total of $2,825.60 per aircraft that utilizes these fluids. Next, the pumping costs usually range from between $400 to $25,000, with most commercial aircrafts generally starting off at about $18,000 to $24,000. Next, because of the huge pipelines or the amount of pipelines required by the system, it usually takes up a very large footprint, and the valves and pumps and reservoirs usually have multiple required maintenances over the period of usage. While the EMA system does not require any additional fluids, the development of the terminology system to manage the system totals to approximately $1,530. No pump is required for the system to operate efficiently, and the footprint, I know I have larger here, but it's supposed to be smaller, is significantly smaller in comparison to the hydraulic systems.
All right, next I'm going to talk about the current application of the EMAs within the aviation industry. They are currently being implemented in a few aircraft, some of which include the Boeing 787 as well as the Airbus A380. However, they're only being implemented in the secondary flight control surfaces and not the primary flight control surfaces. There is a distinct difference between the two, in which the primary flight control surfaces are the critical flight control surfaces that help to control the trajectory of the aircraft. So we're talking about roll, pitch, and yaw of the aircraft, as you can see by this image here. The secondary flight control surfaces are the control surfaces that help to control the lift of the aircraft. And part of the reason why they're not being implemented in primary flight control surfaces or throughout the entire aircraft is because of the fact that, for one, the reliability of the system is still not fully known, since it's still relatively new within the aviation industry. But there's also a thermal challenge that needs to be addressed here. When an EMA is operating in an aircraft during a complete mission cycle, we do notice that the amount of heat that it generates, it varies over time as a result of the variations in the actuation force that it will need to provide for a particular flight cycle, which I will go into a little bit later. But because of that, the amount of heat that's generated is actually a really large amount, so that needs to be managed well. And then another challenge here is also ensuring that we're not trying to reintroduce any type of hydraulic lines when we're trying to develop a thermal management system here, since we're essentially eliminating it when we get rid of the hydraulic lines. And tying into that, our main focus that I would like to specify is we're looking at specifically the thermal management aspect of our project.
Okay, that's why we experienced some technical difficulties.
So essentially, our research objective here then is to try and develop a passive thermal management system that will be able to maintain the EMA temperature below 85 degrees Celsius. We also wanted to develop a mass, volume, and cost comparison with our EMA thermal management system with hydraulic system.
So, as Mariah touched on earlier, the operation of the EMA produces a sharp burst of heat energy. And to address this, we decided to model and design a PCM, heat piped system design. PCM stands for phase change material, which has a unique capability of storing a large amount of latent heat. Then what happens is that once it gets to a certain point,
the PCM or phase material changes phase and goes from solid to liquid, which releases the heat. Now, if we don't have heat pipes, which are highly effective heat conduction elements within the system, the heat energy generated from the EMA will be dispersed strongly or significantly back to our system. So the introduction of our heat pipes are designed or aimed to remove that heat away from the PCM and the heat generated from the heat pipes. This will ensure that our system operates at a quite effective level, maintaining a proper temperature that it doesn't fail when time period.
So next we're going to talk about our measures of success. But before going into that, I'm going to talk about the flight mission cycle. So here are the mission phases if you look at this table, in which it consists of the stall, climb, cruise, combat, then back to cruise, descent, and stall 2. Combat is going to be where the EMA generates the most amount of heat. So what we essentially wanted to look at for our project or our study is 2 particular conditions. One in which we're looking at the entire flight cycle from stall to combat, and then we're also looking to look at the temperature profile from stall to the very end of the mission cycle, also known as stall 2. So from stall to combat, we're going to name that condition A for the rest of the presentation. And during this stage, the EMA generates a total amount of 245.4 watts for a total of 1,320 seconds or 22 minutes. And then for the complete mission cycle, we're looking at a total heat of 340.8 watts for 2,400 seconds. And we're also going to make that condition B for the remainder of this presentation. And again, what we want to do is essentially maintain our EMA below a 85 degrees Celsius maximum operating temperature for our project. We also want to maintain the overall system cost below a quarter of the cost for a hydraulic system. And those are our indicators for our measure of success.
I just want to go over the literature review.
So in the first paper analyzed was written by Leanne and Lynn. They designed a system that would utilize heat pipes to remove the heat generated from the EMAs. This requirement was based on the high heat generation caused by the velocity and force output from the system. And they determined that the phase in which, or the flight phase rather, in which the most heat is generated is during the combat phase. This is due to the aircraft doing the most maneuvering during these phases. Therefore, the EMA is most active during these periods. So what they proposed was to install the heat pipes on the highest heat generation areas, which are the motor and the driver, specifically the electronic components within the driver. And then they would mount the condenser portion within the aircraft's fuel system, which would reduce or cancel the overall requirement for additional fluids within the system. One thing to note is that this system is the basis at which we started off the design of our system, and we took it in a different direction to enhance the system.
So the next literature review went through with Lawson Poynton. Basically, they went through a research study where did a thermal management system for EMA as well. They went through 3 different systems. One was the thermosiphon and heat pipe PCM combination as well, and the ram air cooled system. So through their research, they actually came to conclude that the ram air cooled system was the most proficient system for thermal management system for the EMA, but we decided to verify that through our own research by actually testing the PCM.
So these 2 papers, although they do address the thermal aspect of the EMA, what we really used this for was understanding what ways in which we can go ahead and simulate and build our testing experimental setup. So that's really the main focus behind these 2 papers. They also purchased an EMA and conducted a study on the thermal and physical behavior. And we also use some of that data to work through what we should be looking at for our final experimental setup.
All right, actually going over the methods and computational procedures. So in order to conduct this research, we actually have to go through various couple steps. First, we have to just receive all the thermal specifications in order to conduct our research. We have to get our all the environmental and thermal specifications. After that, after doing all of that research, we then design a thermal system that will be able to meet those specifications. So we were able to simulate thermal conditions and then build our own test environment and conduct our research.
So as discussed by Pooh, first we had to analyze various conditions, and we started off by analyzing the various flight phases, starting from the stall to the highest level of cruise or combat phase, which is at the highest altitude. Why this was important was that the air quality, being the temperature of the air and the density of the air, varies based on altitude. So as you can see from the diagram on the screen, we can see that at low altitudes, the temperature is relatively warm, which produces a pretty high or good heat transfer coefficient of the air surrounding the system. And as the aircraft climbs through various flight phases, the heat transfer coefficient of the system, or the air around the system, decreases and is at its lowest point at the combat phase, which is about 63,000 feet above, and also is within the same range for both cruise altitudes of commercial and combat aircrafts, being 45,000 and 50,000 each.
So next we're going to go ahead and talk about how we determine the amount of PCM we're going to need for our project. But before going into that, I'm just going to mention that we did end up choosing a PCM with a melting temperature of 56 degrees Celsius, since it is well below our maximum desired operating temperature. And the EMA should theoretically be able to be maintained at 56 degrees Celsius until the PCM fully melts. What we decided to do here was take the conservative approach and actually estimated the amount of PCM required based off of a complete mission cycle. So again, we're looking at a total amount of heat of 340.8 watts being generated by the EMA for a total of 2,400 seconds. And the way that in which we did this was we related the amount of energy that was being released by the EMA by the amount of latent heat that the PCM was able to absorb. And then from there, essentially calculate the amount of mass and volume that we'll need to then go into determining the thickness based off of our enclosure size. So next we're going to talk about our 1D transient PCM model. This is a model that we use to examine the performance of the PCM. And there are some assumptions that need to be made in order to be able to use this, some of which include 1D heat conduction within our model. We also needed constant surface uniform heat flux applied to the inner enclosure of our PCM model, our enclosure. We also needed it to be quasi-steady state, and the amount of latent heat that the PCM has must be greater than the possible sensible heat. And from that, we're basically able to use this linear equation shown at the very top here to look at the temperature profile of the PCM with each linear time step. The first boundary condition was found through the second assumption here of uniform constant heat flux applied to the inner enclosure wall. And the second boundary condition here was found by looking at the liquid-solid phase, boundary interface within the melting PCM. And from that, we're able to find the total equation, which we were able to use again to look at the temperature profile of the PCM. Next, we're going to talk about determining the number of heat pipes. And we were able to do this by essentially looking at the resistance network of our model. But before we can implement the thermal resistance network, we had to ensure that the PCM has reached complete melt or full melt. So and the reason behind that is because the PCM is in transient state during its solidification to melting process. So we had to make sure that the system was in complete steady state system before we can go ahead and implement this. But once we do that and look through our resistance network, we can then calculate for the number of heat pipes by dividing the amount of heat that's left for the EMA to reject over the amount of power that one heat pipe can push out of the area and put into the heat sink. So next, we're also going to talk about the simulation model. We performed analysis in ANSYS fluids, and we did a 2D model for this. Essentially, we imposed a laminar, energy, and melt and solidification model on our model. We also applied the Boisnes approximation in order to solve for the non-isothermal flow that is experienced by the PCM. We also applied a mesh independence test in order to ensure that our results are independent of the mesh and that we are saving computational time. And we found that increasing the number of cells beyond 1,193 was going to result in a maximum percent difference of about 3.1% in the heat transfer coefficient value, which is what we used for mesh independence. And again, we measured conditions A and B and applied the heat flux to this bottom right here. So this is essentially the design for our system here, which Kimani and Corey are going to go over in more depth in the next slide. But the main point here that we want to focus on is the location of our Q-type thermocouples. We placed 4 thermocouples on the body of the motor and 4 thermocouples on the body of the enclosure. But again, they will go into the fabrication process as well as the method.
So initially, instead of purchasing the motor or a driver for an NA, since we're just studying a thermal aspect of this application, we decided to take the route of purchasing aluminum cylinder blocks and aluminum rectangular block, in which we milled to insert a heating cartridge that will produce the heat generated by the EMA, simulating the requirements of the desired system. Afterwards, we mounted the thermocouples, as Maria alluded to just now, in a radial fashion around the cylinder, just to ensure that we can measure the temperature profile at all points in the cylinder surface design. Afterwards, we molded copper sheets into the desired shape of the required casing for the motor. Then we tried brazing here, but that method failed, so we reverted back to using JD Weld to seal and close the system. Afterwards, we showcased the finished enclosure for the motor portion of the EMA, of our cylinder block design.
Alright, so then next we have to actually cap our enclosures. So this is us just creating a circle for the cap enclosure. Then we have to create the fins. We decided to create a fin with 7 holes. I believe there are an inch each. And then there was 6 of those.
So we also implemented the fins to enhance the thermal conductivity of our system because PCM has a pretty low thermal conductivity, just so everyone's aware. And we also used it, it was multi-purpose essentially because it was also something that we were using to enhance the structural integrity of our system since we had to orient this in a horizontal position. So that was also one of the purposes behind it.
Then we have to create the outer enclosure for as well. Finally, you're able to fill in the PCM. We actually have to melt all of it, about 4.2 kilograms. Using Mastermind's oven that we created. So we're able to fill that up. We had to wait for it to completely prime, and then we're able to finally put the top enclosure to seal it off completely, JV welded everything around it to make sure it was fully sealed. So even before that, we actually tested before we put on the PCM, we had tested it with water to see if there was any leaks. Then we put a PCM on.
All right, so this is our system architecture, just so everyone knows what we did. Essentially, we connected a variable power supply to our EMA enclosure, and we used a electricity monitor to measure how much wattage was going into our system. We used K-type thermocouples to perform the temperature measurements, and we used the Omega DAQ module to be able to collect that data. And that's pretty much how our system was working. So this is essentially the final system setup, except the only thing that's different here is we had actually tilted the EMA on its horizontal position, and we also applied some heating cords around the body of the enclosure because the PCM is subjected to a 40 degrees Celsius ambient cabin temperature. So only differences, but otherwise essentially the final.
So this showcases the bill of materials that we use to create the system. Most materials here are already mentioned. Key things to add to that that we probably did not discuss were the electronic digital meter that showcases the voltage that was being sent into the system, and the coiled heating cartridge system, coiled heater that was wrapped around the aluminum casing of the system that created the ambient temperature of the system. Now, it's kind of hard to see here, but the total cost of our entire system amounted to $1,536. And that was pretty reasonable when compared to most hydraulic systems that are out there right now. So, yeah.
Next, we go on to results and discussion.
All right, so again, we used ANSYS Fluent to perform our analysis, initial analysis. And we looked at the liquid fraction as well as temperature contours for both conditions A and conditions B. From condition A, in which that is from stall to combat, and then the other one is the complete condition cycle. We found that for condition A, it was able to successfully maintain the maximum operating temperature of the EMA below 85 degrees Celsius. It actually reached to about 69.28 degrees Celsius. Which is great, that's exactly what we need. However, the PCM hardly melted here, so technically the heat pipes wouldn't be able to operate quite yet. Then for condition B, we found, based off of our simulation results, that the PCM will be able to completely melt. However, it was not successful in fully maintaining the system below that 85 degrees Celsius threshold. We had it reach up to 137 degrees Celsius for condition. All right, so this is our experimental results here. We actually found that this agrees pretty reasonably with our simulation results. For condition A, we were, well, actually, before I even say that, the first point here, the line that's going upwards, which is set of 4, those are the motor K-type thermocouples that are measuring that. And then the last 4 at the bottom are the bottom below. But we were essentially able to find that the maximum EMA temperature was found to be at 68.137 degrees Celsius based off of our experimental results, which is in really good agreement with our simulation results since that's only about a 1.9% difference. And then for condition B, again, it was unable to successfully maintain that EMA temperature below that 85 degrees Celsius here. It actually was a little bit lower than our simulation results. We found the maximum to be at 111.06 degrees Celsius, which is about a 19.13% difference from our simulation results.
So based on the results we received, you can see that decent thickness of 5 millimeter is unsuccessful. Say the temperature and desired range. I believe that PCM was just too big. It might need to reduce the size just a little bit more to be able to. 10 millimeter thickness would be the perfect amount to use, and that would in turn reduce the size of our system as well, for a better environment. We actually had to remove our E pipes in this system. There was no need at all. 10 millimeter thickness, you should be able to better thermal.
And going into that, we decided to go ahead and try to look for optimal thickness using simulations. As Q I just mentioned, we found that 10 millimeters would be the perfect amount of thickness. Before going into that, though, I also want to mention that this is specifically looking into how much PCM would melt from stall to combat phase. We wanted it to be able to be almost complete, close to melt at this stage for this particular condition. And 10 millimeter thickness was able to do that. And the temperature was also able to be maintained below 85 degrees Celsius. So that's why we think this is optimal thickness to go. Again, our simulation results agree pretty closely with our experimental, so we're hoping that if we do this test, we will get exactly what we're thinking for our project. This is also for 5 millimeter thickness, but this one indicates this is not a good way to go. Below 10 millimeters is not great because it will increase the temperature way above that 85 degrees.
So when looking at our system in comparison to the hydraulic system for a specific aircraft being the B747-100, the overall mass of our system takes up about 229.6 kilograms. That is 8.2 kilograms per EMA system. And there are currently 28 different spots or locations in which the EMA will be required. While for hydraulic systems, it would amount to 2,296, which conveniently correlates to a perfect relation of 10 times the size of our system or the mass occupation of our system. And the volumetric data for space or footprint that hydraulic systems is quite hard to find, but our system takes up per EMA takes up volumetric space of about 541.54 cubic centimeters.
Also, bear in mind that with the optimal thickness, which is a lot of what we have right now, the system's mass and volume savings is actually going to be significantly greater. Also a benefit.
So now we go to conclude. So basically, we believe thermal management systems for EMAs is the way to go. But we're successful in creating a system that does in theory actually work for EMAs, but did overestimate initially. And basically, I believe the future work once we have optimized a system that can actually reflect the true mass, I believe this would be the.
Tying into that, we also would like to go ahead and look at other means of fabricating our enclosure, perhaps forging or additive manufacturing, because we did have some issues when we did our initial tests where our enclosure was unable to prevent the PCM from leaking out due to thermal expansion of our copper, and the JB weld was unable to prevent that from happening. Other alternatives to fabricating an enclosure. Definitely. So we had already mentioned everything.
So finally, we would like to acknowledge Dr. Shu and Dr. Kabir, our advisors for this project. They have guided us quite well with their knowledge and expertise in this project. We'd also like to express thanks to the NASA Miro program and to the NASA Miro program for funding our project, as without them, the completion of this project would be simply impossible. Thank you.
Presentation. Any feedback or questions from the audience? Yeah, it's not easy to build something completely from scratch, and also figure out the numbers, the dimensions in each student. So yeah, it is hard work.
Yeah, and we pivoted to this project in early December, late November, so the timeline was quite. So
I hope you learned a lot from this.
definitely.
Definitely. I think something that like we all have learned, especially is we've spent a lot of time in school working through theoretical problems, and when we actually have the chance to then go ahead and build a physical object, physical thing, and we're thinking about things from a theoretical perspective. I think we really realize that like we shouldn't expect that what we're thinking about theoretically will not always be exactly what we're going to get at the end. Because that is also another reason why we overestimated. We were thinking that for the amount of PCM, we theoretically thought that we would be able to maintain the PCM temperature at 56 degrees throughout the entire time that it was still trying to melt. So definitely learning to realize that there's a difference between theoretical and real life is something that like we have all together.
And actually understanding how the fabrication process goes and the failure to bring it back, understanding that some materials might be listed as something while it's actually something else. So, I mean, the building process has been quite a journey, and we've learned a lot across. Oh, I forgot to thank Jaime. We had to thank our TA, Jaime Reyes, who has supported us throughout this entire project. Honestly.
Yes. And thank you to Kevin because he definitely he saw us a lot.
So, yeah. That's what it was. So thank you guys again for listening, and I hope you have a wonderful day.
Thank you.
So, our next group is mechanical and biomedical combined group. So we have three mechanical engineering seniors, Justin, Kai, and Abdullah. We have one biomedical senior, Ocean. Let's work together on this project titled Design and Development of a Low-Cost Arduino-Controlled Bag Mask Ventilator. And this project is supervised by Dr. Dennis. So I don't see Dr. Dennis here, but I guess you guys you're ready. I believe I have your slide. So just make sure you share the slide. And also, just again, remind everybody, please, check the link, fill out a survey to support your classmates. All right, and if you're ready, we can go ahead and get started.
So hello, good afternoon everybody. My name is Justin Ann, and we are the Biomedical Engineering Group / Mechanical Engineering Group for Spring 2022. Mentioned before, my name is Justin Ann, and we'll be presenting the low-cost Arduino controlled bag valve mass mechanical ventilator. Our teammates are Ocean Wilson, Abdullah Amagut, and Ty Roseberg. Unfortunately, Ty could not make it today, but we'll be going on with that one. For our outline, we'll be following this outline. We have the motivation and a literature review, followed by the key requirements that we want to follow for our mechanical ventilator, our materials and methods, the results that we got, our bill of materials, the cost comparisons to existing ventilators, size comparison to existing ventilators, our conclusions and future work, and our acknowledgements. So for our motivation, we wanted to address the issue of COVID-19 patients with suffering from acute respiratory distress syndrome. Acute respiratory distress syndrome basically lowers the amount of air that can go into a patient's lung. Patients with ARDS require breathing assistance from mechanical ventilators. However, traditional mechanical ventilators are expensive. Therefore, we wanted to find a solution to the shortage of mechanical ventilators and to avoid the expensive cost of those mechanical ventilators for COVID-19 patients.
So in order to complete this project, we had to do a lot of literature review because we had to understand, okay, what is it we're going to build and how we would go about doing it. So our first literature review was basically one that helped us to understand the different lung mechanics that are involved with this system. So, for instance, we had to get an understanding of what is the effect of pressure on the system, volume, and flow. With these, we also had to find out what is the relationship between these different factors and how will these factors affect the system. Our second literature review deals with the log parameters. So some of these parameters includes like tidal volume, inspiratory volume, expiratory volume, and the lung capacity. If you look to the diagram here to my right, you'll see a graph. And this diagram is basically representing what I am doing right now. So I am carrying out the process of respiration. Here you can see the inspiratory volume. So when I inhale, the volume goes up, and when I exhale, the volume goes down. Where you see residual volume, that is basically air that is left within the body, because when we carry out the process of respiration, not all of the air is exhaled or expelled. Our third literature review helped us to understand, okay, we're making a ventilator system. How will we build this prototype? What does this prototype consist of? Where will we put the devices or the materials that we need to build this device? So we dive into the mechanical operations of the ventilator system, and also this paper helps us to understand that you have different types of mechanical ventilators. And with these ventilators, you have different sizes. They range with different costs. The lowest one can be about $5,000, and it can range to approximately $50,000. And last but not least, our final literature review that we looked over was one that helped us to understand, okay, we wanted to meet the FDA, we were ambitious to meet the FDA requirements. And this was a literature review that tried to meet the FDA requirements as well. And it also gave us an insight of what the cost of our ventilator system might be. It can be, our aim was to build a low-cost ventilator system. And this literature review also had that aim as well. So it gave us an insight of what kind of materials we can use, or will we place these devices and materials together to actually get a working system.
So in designing this prototype, there are several key requirements to follow. The first of which, how far the amber bag should be compressed downwards and how frequently it should be compressed. The amber bag should be compressed 1 to 6 inches every 6 seconds for an adult. The other requirement that we want to follow was the FDA ventilator requirements, as seen in the table on my right. These ventilator requirements, the values in ventilator requirements are the parameters that we use for our simulated test log that we make through MATLAB. This will be expanded upon later on, but these are the parameters that we use for our test trials and our bench experiments. So we wanted to, first equation that we wanted to, I guess, use or determine, first factor that we wanted to determine was the downward force necessary to compress the bag. This was done by using the equation FP, which is downward force equal to the pressure times the area, the contact area, plus the inherent self-inflating force of the bag. So PB is definitely the pressure in the bag, which is assumed to be 40 centimeter in H2O, and the A is the area of the contact area between the lever arm and the bag. Next thing we wanted to focus on was how is the motor torque affected by the strength, the stroke length of the motor that we use, and how does the angle affect it as well. In diagram to the bottom right, in diagram to the bottom right, we can see how the stroke length, so as the angle increases, the as the increase in the motor torque increases as well, and at different stroke lengths, the torque that is produced also increases as well. Diagram on the left shows basically how the how the motor torque interacts with the system, how the system interacts with each other. Next equation that we want to look at was how the volume changes during compression. We derived that the volume would change as the distance d becomes closer. The distance d is determined on the center of the motor arm and the center of the bag. As the distance decreases, which is 0, we will obtain a maximum tidal volume of 1,225 milliliters. And as the distance increases, so as the motor arm goes away from the bag, this tidal volume would decrease as well.
Hello everyone. Here, as you can see, our prototype. I will talk about the prototype and the problem we had in each one of them. The first prototype, the lever arm was heavy, and it doesn't push the bag all the way needed. And in the second prototype, we made it smaller, weightless, but the problem is we didn't have space for the actuator. So we moved to the third prototype with the design helped by our TA Jaime. Third prototype, we attached the motor, but the problem is the stroke length. The stroke length for the linear actuator is too short. So we moved to the fourth prototype. As you can see, it's used a different material and it's lighter, and that was one of our main goals, to make it lighter. But the problem we had with this one is the motor gear by itself didn't provide enough torque to compress the bag, and you will need also another force to compress the bag. And this is the 3D model design of our latest working prototype. We used Shaper 3D software to this close view of the prototype design and isometric view of the prototype design of the hood.
So in designing a prototype, we use the following electrical architecture. We have a 12-volt battery pack, which is connected to our geared motor driver, the L298N motor driver. This motor driver allows us to change direction if necessary and the speed of our gear motor. We then use a potentiometer connected to our Arduino to change the speed of the gear motor. And in a separate system, we have the flow head and pressure sensor, which is read into our computer. This allows us to obtain our pressure values when the system is operating. So this is the final product. This is the final prototype, or this final prototype when it's all connected together. It uses an oscillating cylinder mechanism. Therefore, as the lever arm rotates due to gear motor, as the connecting arm rotates due to the gear motor, the lever arm would compress the bag, and it would rotate in a rotary motion, so it would basically compress the bag every 6 seconds as we tighten. And the pipes that we use, which are PVC pipes, use a telescopic mechanism, which are basically go back and forth beside each other. So this is the timeline that we of our prototype design. As mentioned before, we went through our first prototype. We finished our first prototype around end of January. Then February we came up with we went on to do our third prototype in February. So and our final prototype actually was just recently finished around mid-April.
Creating this prototype, we had several limitations, but one of our biggest limitations was that we did not have a test run. So that being the case, we created a simulate model using the MATLAB simulate package. There are several model parameters included with this simulate model, such as the RC, which is the central area resistance, RP, peripheral area resistance, and different types of capacitance. The resistance is just basically that force which hinders the air from flowing within the system, and capacitance is just the ability of the lung system to stretch and expand. After we've created the simulate model, using these model parameters, we did a test run on our system to see if the system was actually working. Now, so these parameters that we have are from the FDA table, which we use as a guidance in getting these results. And from the figures here on the screen, you can see where we got the input pressure graph, the output flow, and the tidal volume. And we achieve a tidal volume of 500 ml, which is actually an ideal tidal volume for an adult. This next slide shows the simulate model when we added our ventilator system to it, and we got 2 results. Now, for this specific test trial, we decreased the breaths per minute by 50%. Now, with that system, that is a lung system that is actually going through some sort of difficulties, for example, maybe COVID-19, which was one of our aim why we decided to do this project. And you can see that the tidal volume for the under-inspiring lung, which is an unhealthy lung, is actually at 250, and with the help of the ventilator, it was raised to 500.
So using the parameters from the FDA table, we did 8 test trials, and our results, we obtained 8 test trials. We did 8 test trials, and with an intended tidal volume, with different intended delivery tidal volumes. So from our bench experiments, we obtained the experimental tidal volume column down there, and our percentages. We intended to deliver 500, but we had differing percentage differences. So, for instance, in our first test trial, we only managed to reach a peak tidal volume of 331 milliliters, as opposed to the 500 that we were intended to reach. So we had a 33% difference in our tidal volume. The reason being is that when it is lower, I believe it requires a faster. The system would have to be faster to pump more air into the lungs or into the simulate model. And if our percentage difference is actually positive, we would actually need to slow down the system, as that means that too much pressure is being delivered to the patient. So for our results, we selected two of our test trials, and using the following parameters, using these parameters. And on the graph to the far left, we can see how the pressure changes in accordance to time when our ventilator is being used for the system. So the increase in pressure is due to the one pump basically going through that system. The graph in the middle shows the flow rate, and the reason why it goes between positive and negative is because as it goes positive, that means positive means inhalation, and when it goes to negative, it means exhalation. Okay, and the image to the far right shows the volume change as time goes on, as the time goes on, and from this tidal volume graph, we obtain our peak volume of 331 milliliters. So in our second test, similarly, we can see how the pressure changes in accordance to time, and our flow rate graph and our tidal volume. And from this, we're able to obtain a tidal volume of 461 milliliters, which is closer to the 500 that was intended to be delivered. But the percentage difference was about 10%, I believe. So for
this is a table showing the bill of materials This include all of the materials that we used to build our prototype. And as we stated before, one of our aim was to build a low-cost ventilator system. And as we can see right here, our total cost was approximately $300, which is safe to say that we have accomplished one of our aims. We also then go ahead to compare the cost of our ventilator system to other ventilators, and we are still within the range of being a low-cost ventilator because, as you can see, the Puritan ventilator costs approximately $47,000, and the Care Fusion ventilator costs $19,000, and we are approximately $300. So that's a good look for us. We also took into consideration the size and the weight of our ventilator system because we wanted it to be portable. And our ventilator system weighs approximately 8 pounds. And when compared again to Care Fusion and Puritan ventilators, we still have a lighter weight than those other ventilators, which means our ventilator would be easier to transport.
So in conclusion, our results were comparable to existing emergency use FDA-approved mechanical ventilators. We're able to build a simple and easy-to-operate ventilator with readily available components. We're able to control the speed of our actuator actually. So therefore, the breaths per minute could be adjusted as well. And similarly, because of its low cost of being less than $30, our design could potentially provide a ventilator solution in resource-constricted environments. So for our future work, we determined that we wanted to go for a lighter build, so therefore 3D printing could be an option for us in the future. And we wanted to make the design modular so that we'll be able to pull it apart and put it back together easily or fast. We wanted to implement alarms or alarm systems and fail-safe systems. Therefore, if the tidal volume of a patient goes over or under a certain limit, the system would give a warning, whether in the way of a sound or a light. We want to complete our electrical system by adding an LCD screen so that we can display the breaths per minute, the pressure, the input pressure, the output pressure, and the flow running through the system, the spirometer pipe. We want to test our system and compare it with results from simulations and from an actual test lung system. And we want to make it go through, if possible, a 24-hour test, as that is a requirement to pass FDA approval, as the system must be able to operate for more than 24 hours. So, in acknowledgement, we'd like to thank Dr. Shu, Dr. Kabir, Dr. Dennis, and our TA advisor, Jaime. I'd like to thank Kevin and Dr. Mr. Pablo as well for helping us in the machine shop. Yeah, and then without them, we would have made this far. Thank you again.
By the way, great presentation. Yeah. If the link doesn't work, we will try to copy that. While they are working on the video, any questions, feedback from the audience? Yes.
What was the most challenging aspect of your project for each person?
For each person. Okay, so for me, so for me, it was definitely working in a team environment and basically coming up with different ideas. Because typically, I came up with like the first 2 to 3 designs, and when I tried them, it failed. So it was just a process of like learning and failing, learning from the failures that I did, and definitely I think some people put more work than others in the group, but you know, I think it was a challenge that I learned a lot from.
For me, I would say one of my challenges would be actually understanding how this system really operates, because seeing the ventilator system and actually trying to build one, that's 2 different things. So I would say I gain a lot of knowledge as it relates to that area. But also another challenge was actually being able to like work with a team, because talking to your friends and working on a team to achieve a common goal is actually difficult sometimes, but I guess it was a learning experience for me.
Actually, one of the things that I learned a lot and improved when working in the machine shops and building the prototypes and like finding the problem with each one and trying to improve it in the next prototypes, working during the sprint, you know. But we learned a lot of things and different skills for my group.
Good job, guys.
It's a good year.
We don't have time to share it. Thank you, everybody.
We can send the links to the chat.
Oh yeah.
So people online can watch it. It works, right?
Okay.
Yeah,
Good job, guys.
It gave us results.
Is this going to be your next step for the master project?
I'll think about it.
Okay. Yeah, we have one last group here for mechanical engineering capstone. Doreen, Davis, Toron, Orlando, Deshaun, please come here. They are working on a project titled Design of an Improved Vertical Spiral Closed Loop Geothermal Heat Chamber. And just a reminder, those still here and those online, please fill out your survey.
Yes, we did.
For this past group. Okay. How about this plugin? It doesn't work. You have trouble with that. If you can stand closer to this one.
And that's the microphone.
That's the microphone.
Like in between the screen.
If you're on here, yeah. So go closer to this. Okay. Yeah, ready? All right, ready?
Yes.
Go ahead.
All right. Good afternoon, everyone. My name is Deshaun Adams. This is my colleague Dorian Davis, Taran Malhotra, and Orlando Bowman. And today we will be talking about the design of an improved vertical spiral closed loop geothermal heat exchanger. Right? Our advisors were Dr. Shu, Dr. Cabrera, Dr. Gibre, and our TA advisor was Jaime Rui. This is our outline right here. We'll be going through these topics. So what is geothermal energy? Geothermal energy is the energy stored in the Earth's crust. This thermal energy is stored in rocks and fluids in the center of the Earth, as you can see right here. And there's 3 different temperatures. First temperature is greater than 150 degrees Celsius, which deals with electricity generation. The second temperature is 90 to 150 Celsius, which deals with heating and cooling, heated fish farms, and heated greenhouses. The last temperature is less than 90 degrees Celsius, and that's just for therapeutical and recreational use. As you can see in the picture up here, we have the direct use, which is part of geothermal energy, binary power plant, flash binary power plant, hot springs, and then on the side right here, you can see the heat pumps. We're going to be focusing on geothermal heat pumps. So there are 2, what is a ground source heat pump? Basically, a ground source heat pump is a pump or a system that uses groundwater or surface water as a heat source or a heat sink. It produces heating and cooling by using the working fluid. And then these loops are a series of buried pipes below the frost line, which is about 15 degrees Celsius. Secondly, there are 2 types of geothermal systems. There's an open loop system, and then there's a closed loop system. For the open loop system, a geoloop refreshes the working fluid underground, using an underground aquifer or freshwater source. Closed loop system recirculates the working fluid, as you can see right here. Next slide.
All GSHPs work under the principle of isothermal conditions. So the temperature below the frost line is constant throughout the year. So in winter, ground serves as a heat source, and in summer, ground serves as a heat sink. Geoloops are the key to geothermal heating and cooling, and the pipes are buried underground below the frost line, and they connect to the geothermal heat pump in the earth. As you can see in this figure, this is the house, and the geothermal heat pump is connected there. So, like all air conditioning systems, GSHPs provide us with heating and cooling modes. In the heating mode, water absorbs the heat from the ground. The geothermal extracts the heat from the water to heat the cold air. So, and then the cold water is dumped back to the earth. In the cooling mode, the process is reversed.
All right, so for our goals and objectives, as we know, there are several problems that most geothermal systems encounter. They encounter insulation problems during the installation processes. So our objective is mainly to resolve some of these known issues, preventing feasibility of the geothermal system usage in urban markets and environments. That is, reducing the area needed for the installation of the system. Secondly, reducing the cost, time, and labor needed to install the system. And lastly, redesigning each component of the geothermal system to achieve these goals while still maintaining efficiency and functionality of said system.
So these are literature reviews we found to help us to design the system. So one paper was from Tequila's team. They proposed a compact ground source heat exchanger. It'll did all that. So they used additive manufacturing. All that eliminated the need for heavy artillery. However, unfortunately, they ran into some flaws. The system ran into some flaws. So So we are going to attempt to fix this. So another paper from Aresti et al. was discussed spiral coils as opposed to conventional U-tubes. Because our paper is also doing spiral coils. Next slide. Now, another paper from Warner and his associates, they use shallow boreholes that it can be as effective as opposed to deep boreholes. Because our paper, we want to use shallow boreholes too.
Thank you, Tarak. So why our system, right? We're going to show you why it's better to go with additive manufacturing part and the traditional condenser units. So basically, for a geothermal installation, the overall cost will be about $35,000 plus the cost to replace the distribution system. For our part, $3,500 to $5,000. Big difference. So now you'll have basically about $20,000 or $25,000 in your budget. So if you need to do anything else, you have the money there. Another issue with geothermal systems will be the installation area. They need very large trucks, heavy machinery, large drills, and they need a lot of space. All right. For our part, small space, minimum space, no drilling, no rigs, nothing like that. Your neighbors won't be upset with you, right? And then one of the main things is your boreholes is about 5 feet from your house. So just imagine your condenser unit. This part is replacing that. And so you don't want your system to be too far from your house because you'll never know what happened. Like if something goes wrong, you won't know. So in our case, we have it 5 feet away from your house. Lastly, installation time. Takes about 2 to 4 weeks to actually do the installation. For our part, 2 to 3 days. No matter the size of the house, 2 to 3 days. So you won't be hot too long or too cold too long, right? Next slide.
All right. In the first step of designing the system, it is imperative to ask yourself a question. What size of heat pump do I want? So 20 BTU per hour of heating output per 1 square foot of heating and cooling space is needed. So, for instance, an average house in DC only has an area of 1134 square feet with a ceiling height of 8 feet. In the United States, it's common to use the unit ton when we measure the heat pump capacity. So, in this relationship, 1 ton is equal to 12,000 BTU per hour. For an average house in DC, we just only need 2 tons of heating and cooling. So, in order to enhance proper heat transfer, the industry uses 1 ton of heating and cooling per borehole. So, for our own system, we only need 2 boreholes because we're doing 2 tons. Next. These are the equations to help design our own heat exchanger. So this is the mass transfer. So it's the purpose of the mass transfer is to determine the amount of flow that's coming in the tubes, in and out of the tubes. So that is opposed to other physical properties such as pressure and temperature. So the Reynolds number basically characterizes the flow regime, whether it's laminar or turbulent. So we're going for slightly turbulent because it helps in our heat transfer process. And this is Newton's law of cooling, which will help determine the UA, value of UA. So because we're using the value of UA to find the thermal resistance because we want to find the length. This will help us find the length and the area, surface area. So in order to do that, we also need Nusselt's number for our equation. And the pressure drop is also needed to determine how the proper pressure and temperature of the system. So unfortunately, we tried east. They did that in east, but we couldn't it didn't work out well. So we tried to do the same, it didn't work out well. Next slide.
So our criteria for our pipe design, basically we wanted to make sure that pipe the diameters were met the constraints of the 3D printer, and then our final parameters were able to basically be installed in a small area, provide the correct heat transfer, cost effective, and then the installation was just an easy, simple, small device, right? And from our calculations, we didn't use ease, but we did use hand calculations and Excel to come up with our pipe diameter, the length of our coil, the number of our turns or the number of our coils, our outside and inside diameter.
All right, these are operating conditions for laminar and sided turbulent. For laminar, we got the final velocity of 0.163 meters per second with a Reynolds number of 1,000 and a mass flow rate of 0.00513 kilograms per second. Now in the slightly turbulent flow, we calculated the velocity to be 9.926 meters per second, and the Reynolds number is 5,700. And we have a mass flow rate of 0.0337 kilograms per second of mass. So, excuse me. So this should be about 0.975 meters per second, and it should be 6,000. So, forgive me. So, excuse me this. Okay, so I want to point out that for these, this is like the velocity will be 10 times that because of our SLA printer. So, and
So to get a better understanding of our design and how in situation, the ANSYS fluid simulation software to run the calculated mass flow rate as well as the velocity through a 3D model of our system. But initially we started off with a 2D model, and that's what you see here. So our first model to the left is the static temperature in regards to a 2D straight pipe model with a 3.46 meters. So what you have here is the max temperature was at 288.15, which is what we're looking for, and the minimum temperature, which would be your inlet temperature, was at 273.15. We also want to take a look at the pressure, and you get a pretty steady flow of pressure loss as you go throughout the length of the pipe, as you can see in graph to the right. Okay, so this is just a pressure contour. So you could just see the pressure change. So we were starting off at 4,000 or 4,898.67 kilopascals, and the inlet pressure was 5,197.27 kilopascals. Outlet pressure was 4,867. The contour just shows the reduction in the pressure. And also, in order to do your simulations, you have to make sure you have a level of mesh independence. So by increasing the number of elements beyond 365,000, results in the maximum percent differences. 4.4% into your heat transfer coefficient and your skin friction. Okay, so going into the 3D model. So we then took the result from our 2D straight pipe model and decided to go with a simulation using our actual 3D coil pipe that will be inside of the heat exchanger. So the dimensions of this is the diameter of the pipe is 0.00635 meters, and the length of the pipe, if you were to stretch out the coils, is 3.46 meters. So this right here is your
pressure statistics. So we had the pressure coming in, excuse the numbers there, at was it 1,000? 1,002, 1,002 kilopascals, and coming out at about 0.9. Actually, sorry, those are 8 pascals. So this here just shows the pressure change coming in the inlet, which is on your left side, and coming out the outlet, which is on the right side. So this here is our temperature contour. So one of the important factors that we're looking for within our models to make sure that throughout the length of the coils that you get the correct temperature change as well. So that did work out for us. So we had the temperature coming in at 275.15 Kelvin. That's about 2 degrees Celsius. And coming out at 288.15 degrees. Yeah, 288.15 degrees Kelvin, which is about 15 degrees Celsius. And that'll give you, basically that'll give you the complete temperature change that you're getting from your ground heat source throughout your working fluid in the system.
All right, so moving into the design process, we kept 4 main points in mind. Initially, the design should be able to accommodate the sufficient piping for the heat exchanger, meaning that it should be able to, there should be 3 channels in this heat exchanger. Secondly, the design should be sufficient for drilling, meaning it should be able to puncture, drill, and stay mounted into the ground. Thirdly, the assembly should not require technical knowledge, meaning you shouldn't have to be a mechanical engineer to use this product. We're trying to make it as simple as possible. Fourthly, the system should be easily assembled with minimal parts, meaning there should be no screws, there should be no use of Allen keys, no external factors in this assembly. Moving into developing the threading for the drill bit, which is also our heat exchanger, we took the concept from 2 manufactured products. One, a ground hook, and second, a drywall screw. The drywall screw because it's known to practically puncture and drill and mount itself into hard surface, which is the wall. The ground hook now is something you dig, something you put into the ground, and it's supposed to withstand a reaction force of about 10 pounds, and it's like 1 inch, so we took the idea from that also to implement into our heat exchanger. So to the top left is our 3D model of the heat exchanger, and we'll be going through the working principle. This device is used to transfer heat, which is the energy. And the purpose of this, the coilings on the outer edge of this part is to effectively drill. The extension is used to further submerge this heat exchanger into the ground so it can go below the threshold of 5 feet, because that's where constant temperature lies. Lastly, the collar is used to connect the drill to the rest of the part and transfer torque so we can effectively drill. So, all right, so this is a hidden line view and a isometric view of the heat exchanger. Suppressing the threadings on the outside, you can see the double coils on the inside showing the clear path for flow, and that's what we practically use to transfer on. On the left shows the collar with the locking mechanism underneath, and to the right shows the extension with the locking mechanism on top. We didn't show underneath because it's practically the same as the locking mechanism with the collar because they all coincide, they all meet, and we'll show further on in the presentation. So this is the assembly of our part, a 3D exploded view, isometric view of it compiled, and a hidden view of this part of this assembly. So this is the design with the specifications. I apologize because we can't see some of the dimensions. But this shows how each and every, well, it gives a perspective of the size of each part, and it gives the perspective of how it locks together in a sense. We'll dig further on
go down this line. All right, so throughout the design process, what we did initially, we placed a cap onto the design, which we found out that was not feasible. That didn't really make any sense. So that highlights in the far left image to the left. Moving on to the gray resin prints, we realized that we neglect pulling the part out of the ground in case of any defects or any damage while drilling. And that is where we took into consideration the third design. In the third design, we ensured that we printed all three components so that we can properly test the assembly and know that each part can lock sufficiently and actually twist when torque is applied. The last print is what we currently use, taking into consideration pulling the drill back out, spinning the rotation of the drill to get it back out the ground, and also doing analysis on the collar to ensure that it does not break while drilling.
So initially, our design was made to be printed in, it was made to be 3D metal printed. So at this point in time, we are actually looking to do that in our future works. So here we have this slide that shows basically the specifications of doing the 3D print in metal. It uses a 4,000 watt laser to center the metal particles together. It's between 5 to 60 micrometers diameter metal particles. Basically, our part will be printed in Miraging steel. It uses extensively high-performance industrial engineering parts, such as aerospace and motor racing applications, and it consists of high nickel and low carbon compositions. So the fabrication requirements the Miraging steel MS1. The gas processing is nitrogen. The power of the laser is 400 watts. The thickness of the layer or the printing layer would be 40 micrometers. Your Material Magic software to upload your 3D model design. That 3D model design can be generated at CAD interface software.
So for the materials and methodology, continuing, we use the rigid 4000 resin. This resin is used to designing engineering applications. Furthermore, it's specially designed for stiffness and precision and general load-bearing applications, and this is also highly resistant to deformation over time. And in the table lies the specifications for this for 4K resin.
All right, so for our collar was mainly supposed to be printed in metal, but we had a resin part, and so we had to do this fusion test to make sure that the collar was strong enough to drill a heat exchanger into the ground. And so we did multiple tests, and initially we started off with this design. We found out that there were some weak points in it, and because of those weak points, we had to redesign. And so once we figured out the weak points, we added more material, we added a different design to it, and we came up with this. This seemed to be the strongest design for our collar at the time, and we've used it, and it's shown to be actually the strongest because it didn't crack, it didn't. When we put it on the drill, nothing happened. And you'll see later on. I mean, in that experiment.
So in regards to our results and discussion, so one of the major aspects to a successful design was being able to put the components together and actually be able to drill into the ground or into some type of ground type material. So we use just some regular soil, and as you can see, the components on the far left. So you have your heat exchanger and your extension connected there, while you have your collar connected to the auger drill. In the picture to the right of that, that is basically a view of us actually doing the drilling, and you can see that given the design is strong enough and capable of staying together while being drilled into the dirt and actually getting the heat exchanger fully submerged into the dirt, which is important as you want to make sure when you use this system that you're able to get it down to that constant ground source heat level. And then going to the right, so we got a little ambitious, and so this is actually some lunar highland material, which is a lot stronger than your regular soil. And as you can see, this was us drilling at about 75% of the heat exchanger was able to get through there. And then we were able to crank up the power a little bit more and at least submerge the full heat exchanger into that material. So our design is strong and able to actually drill it into soil.
So this is just experiment on a heat exchanger. So we hooked up a small little system and ran fluid through it. We can test for thermal, but we could test for flow rate. And so we have a power source right there. We have the heat exchanger connected right there. And as you can see, the water is draining into the bucket. So we transfer the water. We had some leaks that we tried to fix. We couldn't fix them, but we was able to show that the channels do work in the actual heat exchanger.
So this highlights our BOM. It shows the collective and individual pricing of each part that we used in our design. And as you can see, the total cost of this is $1,607. Disregard the cent. And this is, might I highlight, way less than a regular or a traditional geothermal system.
So in conclusion, our helical geothermal heat exchanger was designed to achieve replacement of heavy machinery. So basically, by coming up with the design, we're able to take out a lot of the machinery that you have to spend your money towards and just use 3 components in order to do your geothermal sensor implementation. The possible dimensions to accommodate this system were optimized to create a drill bit that would be able to drill a hole into the ground, insert the piping of the heat exchanger, and by removing the collar, which is attached. So basically, we wanted to make sure that all our components were able to work together to actually get the heat exchanger to the ground. So one of the things that we were able to see was that with the 3 components, had an interlocking system that allowed them to continue to lock and drill into the ground. As you saw in the pictures that I showed before, you are able to get the heat exchanger down to the necessary depth. So that is success right there. So we had a secure flow path throughout our heat exchanger, throughout the channels. The printing constraints have been met. So we had printing constraints as far as the 3 resin printer, which was 8" by 8". But we were still able to get our components printed. And it is, as I said, proven and dig and stay mounted by scale. These parts were manufactured, and the prototype has been tested and studied for proper flow rate, pressure drop performance. That's what the video showed.
Future works. Well, we're going to continue to analyze our system. We are going to, now that the the metal printer is up, we're going to try to print, not try, but we are going to print our heat exchanger in metal, and hopefully we can show it to those that are around once it's done. With the help of Dr. Shu. Acknowledgements. So first of all, we want to thank Tekili. He was instrumental in coming up with the idea. This is his baby. We just took it from him and gave him, designed a better way to get it into the ground. Thank you, Dr. Shu, for all your help. We really appreciate it. Jaime also, he was instrumental in our design, mainly with the printing process. That was very tedious, but we were able to come up with a part. Thank you to Dr. Cabrera and Dr. Cabrera for the insights that they shared with us, and then thank you, UDC, for Miro project funding that helped us with the research project, helped us with the funding.
Any questions?
I have a question for you guys. You kind of touched on it a little bit at the end there, but first of all, what is one of the major differences? I saw you had it submerged in the soil first and then the lunar soil. What's the major difference, I guess, between what we think of as soil here versus on the moon? And then secondly, about printing, you printed in resin and then you said you're going to print it in metal later on. Is there a particular material that would be ideal?
The material that we have right now is the Mirage steel. That's the most ideal at this point. We do have the machine ready, or we're prepping the machine right now to get the process started. And again, Mirage steel is that. All right, we can use probably maybe like a copper material or something else with better conductivity, thermal conductivity. But what we have what we have right now is Mirage steel, and that's what we'll have to use. So maybe later on if we could do. Yeah, on the metal 3D printer.
And you also want to think about cost, and the project still is affordable as well. So among the list, good choice.
Secondly, the difference with the regular dirt and then the lunar soil was the regular dirt. It was a little compressed, but we were able to get into the soil with our part. With the lunar soil, there was a little kickback because there's static. Like once you get to a certain level in the lunar soil, it kind of locks itself together, and so that's why we were only able to get just the heat exchanger. First of all, it was a shallow bin, and we didn't want to crack it, so that's why you only see the heat exchanger in there. With the dirt, we had the heat exchanger and the extension inside the dirt. It was, again, the properties are different. The lunar soil is very at the initial part, at the initial top soil, you can get through. Once you get into like the middle, it starts interlocking.
It's finer, so it kind of like starts to compress.
Much finer.
It compresses itself and it kind of locks. And so you got to exert more force to get down into that soil.
Definitely a lot easier to dig into the soil.
More dry, less humid compared to the soil you used.
Yes. Any more questions?
Yes.
I asked this to the previous team, but I'm actually curious to know, like, what is the biggest challenge for each of you guys during doing the project?
I'll let them go.
The biggest challenge for me was when I did the equations. I tried putting in the software they used, but it didn't work out for me, and I still didn't know how to figure out. But like you said, Mariah, what you learn theoretically isn't the same as in reality.
Yeah.
I would say for me, it's a journey, through the whole process. First, coming up with the idea, and then, there's so many components or so many different aspects that you have to think into or that you have to look into in order to make sure your design is valid or a good design. Then you have your calculations, you have your simulations. I mean, I know I was working with simulations. It was it's definitely a experience, but a very learning experience. And I mean, even with Creo, just the whole process You know, it's a very in-depth, you know, project, but as everybody is saying, you know, you learn a lot. You know, you have people that's always supporting you, so that's always good. You know, great group, you know, great advisors. So, yeah, you know, it's just all around experience.
So even though the project was overall difficult in a sense, the most difficult part was actually getting the required length of coil in that small heat exchanger, in that small shell, let's say, because that had to be wrapped numerous times and then had to be at a specific angle so liquid could flow, and then not too solid so we get minor and major losses. So a lot to consider in that sense. So that was the hardest part.
All right. The hardest part was scheduling. I had a lot of scheduling issues just with the groups because we had one printer, we had multiple parts that we wanted to print. The parts kept failing, stuff kept happening, but we just kept at it. We had great advisors, people helping us out, and we were able to come up with a partially successful part. We want to print in metal, and once we do print in metal, that we feel that we were successful. So.
Just one quick question.
Yeah.
You probably mentioned it kind of stepped up for a quick minute, but what was the change that you made to change, basically make a successful design, and like what was the average time for each print?
So you want to take this? I'll let you.
Yeah. Well, you're talking about for the 3D resin print?
Yeah.
So I would say the average time per part given. So we went through different sizes. So initially we started off with just printing the first the top 4 or 5 inches of each component, you know, and those took maybe almost a day to print. Then after that, then we went to a smaller model just to see if we can, you know, get our pieces attached. And I mean, I think that took 11, 12 hours. So actually, no. So the initial parts that we printed with just the top probably took around the same time, about that 11, 12-hour range. And then when we did our full scale print, that was 20 to 30 hours probably. So
all in all,
he asked what we changed in the design, like coming up. So initially we had a straight top for the cap that could not work to fit the shaft for the drill. So we had to enlarge that. When Dushan did the simulation in testing if it would bend or not, we realized we had to thicken that as well. So we had to thicken that part as well. When we looked into the drilling process, we realized we could not just place each part on each other. We had to place and lock. So we had to think of a locking mechanism also and implement it into that. Along with that, we also made straight coils just to accommodate what was in the simulation. We realized we had to use the maximum amount of space as possible in the shell. So we had to revamp those coils as well. And then lastly, as to accommodate the print for the metal printer, we had to print it upside down. So each threading had to be at a 45-degree angle, less overhang or less the chance of overhanging the print being messed up. So,
so all in all, 3D printing, make sure you know what you're doing. It is a process. Don't try to print all your parts in 3D printing because it's just going to be, you're just depending on the machine. Like it's not your hand. You're not building it with your hands. So if the machine fails, your part fails, and you got to start over.
So you're printing with the merging steel, are you printing all the parts or just the outside, the drill bit, basically?
We're gonna print the drill bit, and then if you have time, we'll try to print the extension as well.
It's a little expensive.
Yeah.
To print everything.
I was gonna say they're big parts. Yeah.
Yep.
All right, thank you guys so much. Again, those folks online, please fill out the survey for this final group. I think I see about 3 groups still left here. Can we get pictures of each of you in front of your posters, maybe? Would that work? Okay, excellent. Thank you, guys.
Thank you. I already sent you. Thank you. you send the recording?
That no, she have that's a web I don't have a access.
You didn't record. Oh, okay.
She is the one recording it. They should send it to her.